Mark P. Otten back with you. Okay, welcome to your multiple regression video. This is the extended version. As I have done with my data screening video, I have a shorter version of the multiple regression video as well for my undergraduate students. This one is intended more for my graduate students who are working with larger data sets. Sometimes you might have heard multiple regression contrasted with simple linear regression. I don't think any of this is simple or should be treated as such, but that's what I'll call it, I guess, for the purposes of this video. Okay, so we're going to start with your simple linear regression, which looks like this, and we're going to go from there. So in this model, we have one independent variable and one dependent variable. The x is the independent and the y is the dependent variable. And then the b is the slope, and that describes the relationship between x and y. The larger the b, the stronger the relationship. So we've covered this already. Moving forward from here, we need to, in order to convert to multiple, so the multiple in multiple regression stands for multiple independent variables. So you're going to see more than one x here. And so in order to be able to compare x's, which is the cool part of multiple regression, you can compare the independent variables to each other to see if one has a bigger effect than the other, or vice versa. So in order to do that, we need to standardize them, typically. We don't actually need to do this if we already have two independent variables that are both on the same scale as each other, but that is relatively unusual in the psychology literature. Usually you're comparing two independent variables that may or may not have the same scale. And so to get around that, we just sort of standardize both of our independent variables. That means putting them on a normal curve. So when you standardize something, you take the z-score of it, meaning you subtract each value from the mean of that variable and divide by the standard deviation, thus standardizing, putting on a standardized scale. And so if you do that, you are able to then compare your independent variables to each other, as we'll see in a minute. Meanwhile, we call the standardized version of b beta. That is again, your normal curve version of your score on that particular variable. And then the alpha is the standardized version of A. Now, alpha typically drops out of the equation at this point. So you're going to have like a beta there that you're going to interpret, and then the alpha just kind of becomes 0 typically. And you can interpret A still, but alpha usually just drops out. So that's the way it goes typically. But then the betas become more meaningful because, like I said, you can compare them to each other. So here's what the multiple regression equation looks like. This is 2 or more IVs, so you can actually have more than 2 here. And then if you convert to the betas there, which SPSS and R will do for you automatically, then you can compare them to each other. And then the alpha sits there, but usually, like I said, drops out of the equation. Okay, so we can compare this is what I just said, compare our independent variables to see which one has the biggest influence on the DV. This is very useful in psychology, right? Because let's say there's some behavior that is your dependent variable, and you're trying to predict someone's behavior. Well, there's often more than one cause of somebody's behavior. Sometimes those causes interact with each other too. So plenty of applications of multiple regression as we see in the literature. So here's the first time that I really did lots of multiple regressions myself was when I was working at UCLA as a sort of like a stats data manager for Chris Dunkelschetter, who still is a health psychology professor over there. And I did this when I was a grad student. It was like my introduction to what a gigantic data set looks like with lots of value, lots of meaning. Because what she was doing was trying to predict baby's birth weight from a variety of stress factors. Basically, the application there is how to prepare and how to be during pregnancy for both mother and father, and the influence that might have on the baby's health, which is a very important topic, much more important than the research I tend to do on sports. Well, maybe not more important, but perhaps more meaningful to a pregnant mom, certainly. All right, so here's a really tiny sample of what was overall a gigantic data set. They interviewed hundreds of moms and dads and took lots of questionnaire measures. So this was just a tiny piece of it, and they had lots of anxiety scales that they filled out. So you can imagine a hypothesis here would be that the higher the anxiety for mom, the less healthy the baby is, and the proxy, the way that health is measured here is just sort of a substitute for it, which is baby's birth weight. Generally speaking, the heavier the baby, the healthier the baby, but that's not always true. But anyway, so you might imagine that mom's anxiety has an impact on baby's birth weight, and then dad's anxiety, maybe to a lesser extent, has an impact. Maybe dad influences mom, which then influences the baby, or something like that. And we'll be talking about mediation models a little bit later, so we could draw this up as like a mediation model here as well. But meanwhile, we're just going to hypothesize that mother's anxiety impacts the baby, perhaps in a negative way, and then same thing for father's anxiety as well. So in order to start this out, we need to screen for multicollinearity. Multicollinearity is a fun word to say and a difficult word to spell. It is a check to see that we are authorized to do our regression based on the fact that our IVs, our independent variables, are not too much the same. So suppose mom and dad are like super in tune with each other. When dad is stressed out, mom is stressed out exactly the same amount, and vice versa. That would actually be a problem for us, because then there's too much overlap. And so if we were to try to run our multiple regression, the regression would complain, because it's like, hey, mom's anxiety is the exact same thing as father's anxiety all the time. And so in that scenario, we would need to take one out, maybe combine them together, the IVs. We couldn't run them together if they're too highly correlated. What is too highly correlated? Well, the textbooks, Tabachnik and Fidel, recommend 0.90 or higher as too highly correlated. That is really high. That's just a recommended value. So in your homework, you can apply 0.90 or greater as a rule. But in real life, if you have a 0.85 or a 0.75 or something that's high, but still below the rule, you still need to look into it typically. You still need to figure out why they're so highly correlated, maybe combine them together still or drop one out. So this isn't like a 0.90 is not so much a rule as a guideline here, but for your homework you can use it as a rule that if the two IVs are correlated at 0.90 or higher, then definitely stop your regression. Okay, so the first thing we're going to do in SPSS is do our check of multicollinearity. So here we're going to have, you see your data entered in with mom's anxiety, dad's anxiety, and birth weight. So the multicollinearity check is just a correlation. So you're going to go to analyze, correlate, and bivariate. And as I've already done here, you're just going to put mom's anxiety and dad's anxiety over to the right. Remember to leave the DV out, because the multicollinearity check is just a correlation between IVs. So if you had multiple IVs here, you would move them over to the right, all of them, and you'd have a correlation matrix. But here you just have two IVs, so you're just going to have a single correlation. And so we're going to get the output here. It's going to be a negative 0.199 correlation, which is less than 0.9 in magnitude. I said 0.9 before. I think a correlation of greater than negative 0.9, that is more negative than negative 0.9, would also be a problem here. So it should be in magnitude or absolute value that a greater than 0.9 correlation is the problem here. At negative 0.199, you are below that, and so you're good to go to continue your regression. So we're going to go ahead and do that. The values that we're going to get here are the unstandardized and standardized values that I mentioned before. So we're going to go ahead and get those values first, and then we're going to back up afterwards and look at some of the residuals and some other statistics that you're going to need second. So you're going to go to Analyze, Regression, and Linear. It's the same place that you went for your so-called simple regression. This is your multiple regression, and what I've done here is just move birth weight, the DV, over to the dependent slot, and mom's anxiety and dad's anxiety over to the independent slot here below. And we're just going to click through and click OK and get your basic statistics first, and then like I said, we're going to back up and do a little bit more next. So The key information you need here is in the box at the bottom under coefficients. It's the same box that you would have analyzed or would have pulled from the simple linear regression. It's just there's an additional row for the second IV here. So under unstandardized coefficients in the capital B column, which I never understood why it's capital B, but that's okay. We're just going to go with it. You have your 9.17. That is your A value. Your negative 0.432 is your B1 pertaining to mom's anxiety, and your negative 0.047 is your B2 corresponding to dad's anxiety. If you go across then to standardized coefficients in the beta column, the alpha is blank, so it does indeed drop out here. The beta 1 is negative 0.81, and the beta 2 is negative 0.093. And so in order to interpret those, we can start to compare them if we want, but I'm going to go first to the p-value column here under SIG. You have a 0.108 for mom's anxiety and a 0.812 for dad's anxiety. And so what that tells you is that neither one is significantly predicting the DV. Both values are greater than 0.05, and so I would probably just stop there and not interpret them with respect to each other. However, you could go back and presuming that, let's say, both are significant, you would go back and compare the betas here, and you, in this case, you see that mom's anxiety at negative 0.81 is much greater than the negative 0.09 for dad's anxiety, implying that mom's anxiety has a bigger impact, in this case a negative one, on baby's birth weight, and so you would then compare. However, like I said, both of these are not significant, and in this case it's very likely due to the fact that we only have 6 people in our data set, or 6 families, that is, in our data set. So you would conclude with the p-values being greater than 0.05 and just probably stop there if you're writing this up in a paper or on a poster. Okay, so once you have your regression equation, which we now do, you can use your equation to make predictions about y. Now typically this is a cool thing about regression. Suppose you're trying to predict how much a baby will weigh, in this case, based on mom and dad's anxiety up through the, let's say, the 5th month of pregnancy, something like that. You can actually make a prediction about it based on that information, presuming that your predicted values are having a significant impact on the dependent variable over time or over a larger sample. Now, in this case, we don't have a large enough sample to conclude that our predictors, our independent variables, are doing enough. However, you can still make predictions based on the equation. And so if you're doing this in your homework, what you do is you plug in to the unstandardized equation here using the B1 and B2. In this case, it would be negative 0.432 for mom's anxiety and negative 0.047 for dad's anxiety. Plug those in, and then your A value is 9.17. Use all those values, and then let's say you have a new family that comes along with an X1 and an X2. You can make a prediction based on that family. For in this case, also you can, let's say, take the first family in our data set, the 3.4 for mom, the 2.9 for dad, plug those in for X1 and X2 using the B1 and B2 values from the output, and you would actually make a prediction for that family. And so what you start to see is you can make predictions about the existing families as well, and then compare them to the actual birth weight values or actual dependent variable values, and also get an idea of the quality of your regression equation to see if, let's say, all of your predictions are way off or not, or if they're right on, and that suggests that maybe your equation might be good or bad. And so that's where we're headed with this here as we go through the notes. So what are these things? Well, oh crap, we should have checked them first. These things called residuals are the errors of prediction, or the comparison of the actual dependent variable for, let's say, family 1 versus the predicted value for birth weight for that same family. So here's what it looks like in a chart. You've got your X1, X2, and Y values there in the first 3 columns. Those are your actual values, or your observed values. And then that Y with the hat over it in the 4th column, that is your predicted value. So you would get from that equation there with the negative 0.432 for B1, the negative 0.047 for B2, and 9.17 for A. You would then plug in for that first family 3.4 and 2.9 in for X1 and X2, and you get your predicted value of 7.57. Now that is you kind of like over predicted a little bit. Like the actual baby was 6.81 pounds, but then the predicted value is 7.57. So based on the fact that mom and dad were pretty low on stress, then we figured, well, or the equation figured, well, the baby's going to weigh a lot, and actually it didn't weigh as much as predicted, and so you see the negative 0.75 there in red. That's the value that you get from 6.81 minus 7.57. It's a over prediction, or you overshot a little bit with your predicted value. The second one is the opposite. So the second family is kind of funny. Mom is really relaxed. Dad is freaking out at 8.2, the most stressed out parent of any of the 12 in the data set. So what is this? Well, this is kind of confusing for the equation because it's an unusual family. The predicted value was not too far off, actually, 0.27, just a little bit low. The baby was 8.23, so the baby was very healthy despite dad freaking out. And so you can see that some are over and some are under. The problem here for a regression equation would be if you're just way off on everything. And that would indicate that the regression equation is maybe not that useful. We already saw that in this case B1 and B2 were not significant predictors. So that's a suggestion that maybe the regression equation is not, it's one hint that the regression equation is not that useful. But then presuming that we gather more and more data, you normally see errors of prediction here. So presuming that we're going to gather more data, then the equation might, again, look like a good equation. Also showing you the standardized equation here in the notes. Now I can actually, to be honest, never remember if we standardized and then calculate residuals, or if you calculate residuals and then standardize. But either way, the concept is the same here. You're standardizing your residuals, meaning you're putting all of your residuals on the same scale, and you're putting those on the y-axis, and then you're comparing those to the standardized predicted values from the same equation. So what we're doing here is we're trying to look for patterns. Is our data over-predicting for babies with high birth weight, or under-predicting for babies with high birth weight? Or is there a lot of variance? Is our equation terrible for babies with low birth weight, whereas it's really accurate for babies with high birth weight? These are the things that this graph is going to pick up on for us. And so those are captured in these three things to look for: normality, linearity, and homoscedasticity, or I guess equality of variances. And so this is what we'll look for in our data set in a minute. So the first thing that might jump out of the graph here is errors of prediction that are normally or not normally distributed. So for example, here if you have a baby's birth weight value of 8, that's pretty high. Let's say predicted birth weights based on the regression equation should be normally distributed. There should be some that are like over predicted and some that are under predicted, right? If our equation, our equation is never going to be perfect, so we're going to be making errors of prediction no matter what we do, unless we're amazing, which we are, but the errors will still occur. Anyway, given that errors will occur, you want to see some that are over and some that are under. So for example, if you go to the birth weight value of 8, and you see, okay, some are over, some are under. Generally, the mean is the middle, 8 pounds, and so most of our predictions should be around there, and then they should be falling off on both sides as in a normal curve, right? So the mean is 8. Most of the predictions are around 8, and then they're gradually falling off so that some are 7, some are 6, but fewer and fewer as you get further away from 8 pounds. So you can look at this for 8 pounds, you can look at this for 5 pounds, and the graph is going to show us the following. So there's 4 graphs here. We're going to look at this a couple of times. So these are from the Tabachnik and Fidel book, so if you have that in front of you, maybe it's going to be bigger there. So the top left here is assumptions met. So that's what a regression residuals, standardized residuals plot is going to look like in the top left there, if everything's fine. The second one, so the one in the top right, that is a failure of normality. And so what that's doing is if you look at that one, you're going to see that there's like a cluster of dots above the line, but pretty close to the line. And so what that's suggesting is that there's a lot of predictions that are like slightly over, but there's none that are like way over, if that makes sense. So if you see like a predicted value that's like way over what it should be, it's going to appear higher up in the above the dots there. But we don't have any of those. However, below the line, you're under predicting, and you're under predicting wildly across every. If you go left to right, that's like birth weight. So the left side of the graph is a low birth weight, the right side of the graph is a high birth weight, let's say. So you're under predicting kind of like a lot. There's a lot of under predictions, and they're spread pretty far under for all birth weight values. And then in terms of over predicting, you're over predicting sometimes, but you're only over predicting by a small amount, and that's that cluster that's right above the line. So what is this saying? This is saying that we have a positively skewed pattern of errors of prediction. And so what that means is we're under predicting quite a lot. So if you were to say, turn that graph on its side, you'd see that there's a mean of errors of prediction that's right around the mean, and then it tails off more gradually on the under predicting side than on the over predicting side. So we have a failure of normality. What you would want to see is more like the top left, where you have a cluster right around the horizontal line there. For every birth weight, there's a cluster of predictions around the line, or the actual value, and then you're falling off gradually to the high side of the line, the same rate that you're falling off gradually to the low side of the line. Okay, and we can obviously go over these graphs more in person to clarify some of the questions you guys have, because of course this is not going to be super clear the first time, even with my amazing, astute explanations. Okay, maybe not. All right, so the second assumption to look for is linearity. The relationship between the predicted DV scores and errors of prediction should be linear, so we shouldn't have any nonlinear patterns here. And so I'll illustrate again, to the best of my ability, what a nonlinear pattern is going to look like. So the example here is that our regression equation overestimates weight for a light baby, underestimates weight for a mid-range weight baby, 6 pounds, and overestimates for a 9-pound baby. So this is like we're underestimating for a while, then it switches, and then it switches back. So the regression equation is kind of confused as to what it's doing. So if we're gonna look at an example of this, we're going to look at the lower left. This is a violation of linearity. And so again, as you go from left to right, you're seeing birth weight that's low on the left and high on the right. And then if you were to it's like block this off in 3 chunks here. The left side of this graph, that's low birth weight. You see we're under predicting a lot. So a lot of dots below the line, but not a lot above the line. Then if you look at the 6-pound baby, so the middle of the graph, going from left to right, in the middle you see a lot of dots above the line, which suggests that we're over predicting a lot, but not under predicting much. And then you go to the right, you see the right side of the graph there again for the heavy baby, the predictions are under again. And so this, in this sense, the regression equation might be good for certain weight intervals, but not for the entire population of babies here. So our regression equation is violating linearity in that sense, and we're probably going to want to correct for that somehow, or maybe restrict our range. Say, hey, let's make predictions here, but only for 4-pound babies or something like that. Okay, so that's the linearity example. The homoscedasticity of variance one. Again, you're going across on birth weight, and you're trying to figure out, is there a lot of variance in our prediction for a light baby versus a heavy baby? Maybe our equation is really accurate, meaning low variance for an 8-pound baby, but for a 3-pound baby, we're wildly off all the time, or there's just a ton of variance, or vice versa. In this case, the example says the weight prediction for a 3-pound baby is really accurate, but for a 9-pound baby is not. So variances of errors of prediction should be approximately equal going across. And so we see the failure of this one is in the lower right. And so what we see here is an equation that is normal in the sense that there's an even number of dots above the line and as below the line. But as you go from left to right, you see a distinct pattern, right? On the left side of the graph there for the lower right graph, the left side you see like no variance. Like that looks like all the dots are right around the line. meaning that in this case, the low birth weight baby is being predicted well. But then as you go to the right, the baby gets heavier and heavier, the prediction gets wider and wider, right? So then there's a ton of variance for those heavy babies. So this is a violation again because, well, our equation is doing an excellent job for the left side, the low birth weight babies, but not for the high ones. And so once you violate one of these assumptions, what do you do? Well, in real life, you would go to your supervisor, you would go to your professor in your lab, and you'd be like, hey, I noticed this pattern, and first of all, they'd be very impressed. They're like, whoa, you're actually looking at these graphs and interpreting them. You must have an amazing 524 professor. Well, maybe they won't say that. But anyway, you would go to them, and you'd kind of try to figure out what happened and try to figure out maybe there's something in it. Maybe like you have only 4 9-pound babies, and so no wonder there's a lot of error prediction is because you have just such a small sample. Or maybe something else unusual is going on with your data, and so this is a possible time to diagnose that. And it might not show up in your initial univariate or multivariate outlier checks and so on. That said, a lot of times when you do those checks at the beginning, if you do have an outlier or something like that, and you catch it early, then that might prevent you from seeing some patterns here of non-normality and such. All right, so I need to show you how to get those residual plots in SPSS, or at least the one with the standardized values, which is the one that most often gets interpreted in the literature. So we're back to the data here. I'm going to go to Analyze Regression Linear and go back to where I was before. In fact, you can do this all in one step. I just wanted to separate them a little bit to highlight the different points of it. So we're actually going to go back to this a couple times more before the end of this very long, well, no, hopefully very exciting and straight to the point video. All right, so we're back to the regression here. I'm going to click on plots, and we have in the notes here what is typically done, which is standardized residuals on the y-axis. So that's z resid on the y-axis, and standardized predicted values on the x-axis. That's z pred, and so you put that over. Click continue. We're going to get a graph for our data here, very small sample. The thing about small samples is that we, with a graph like this, we're not going to be able to tell a whole lot. So here you have it. You've got your 6 dots here representing the 6 people. And if we go back to our notes and compare to some of these graphs as examples, we can start to see, like for this sample here, we have 2 dots that are high on the top left, 2 that are low in the middle, and then 2 that are high in the top right. So that kind of suggests what looks like maybe a mirror image of the lower left graph here in the notes. If you look at this lower left graph, you have a violation of linearity such that we're under predicting the low end of the birth weight here in the example anyway, over predicting in the middle, and under predicting on the right side on the high end. Here in the for the example, or for the actual data of the 6 people, we see it's sort of high on the left, and then low in the middle, and then high on the right. So there is the suggestion, the beginning of a violation of linearity potentially here. The others perhaps not so much, I would say. But imagine you add 6 more people in here, and you have a couple of dots in the lower left now, and the trend just disappears very quickly. So I would say with a sample of anything less than about 30, here certainly less than 10, we're not going to be able to conclude much of anything about violations or assumptions being met or not. So if you're putting together a homework assignment based on a small sample, you want to conclude with caution here. Maybe you would say something like, well, since it's such a small sample, our assumptions are likely not met. However, I'm going to continue, and in the homework you want to continue anyway, just for the practice of it. But in real life, you'd probably want to go and collect more subjects and make sure that your data then reflects what is it's the top left, right, that has the lack of violation of assumptions. That's the ultimate goal. All right, so moving forward, I want to show you the R-squared value for multiple regression. You guys have seen this for simple linear regression. For multiple regression, it's also called a squared multiple correlation, which always reminds me, the SMC reminds me of Santa Monica College. That's not what it is. It is R-squared. It's multiple because there's multiple IVs again, and so you're now looking at the proportion of variance in the DV that is predicted by the IVs collectively. And I think this is the best judge for you guys of the quality of the regression equation as a whole, how much your IVs are predicting the DV and what percentage that is. So here's what it looks like on paper or written out. You have those predicted y values that you start with. So if you're trying to figure out what R-squared is here by hand or by Excel, if you're doing these calculations there, you start with those predicted values, which you found by using the equation that's written there, which we went over earlier in the video. Then you in order to get the R-squared, you need to grab the mean for the y values and then the mean for the predicted y values. And so that's what that bar means there, a y bar in the second most column to the right here with the values in it. The y bar there is the mean of the y values, which is the actual y values here. Oops, here. And then we have the y hat bar. There's somewhere in there. There's a joke about a Y wearing a hat and walking into a bar. But anyway, I don't know what the end of that joke is. Y bar hat, Y hat bar. Anyway, that's the mean of the Y hat values, which is the predicted Y values here. So you take those means, you subtract each one. It starts to look like a deviation here. Those are deviations from the mean, and then you square them, and you get your sums of squares. Those are sums of squares for Y values and sums of squares for predicted Y values. And the sum of 1 goes on the top. That is the sum of squares for regression, or the sum of squares for the predicted values. That goes on the top, and the sum of squares for the actual y values goes on the bottom, like so. And so in this case, you get a 0.63 r squared. The interpretation here is that the 63% of the variance in the dependent variable birth weight is predicted from the mother's and father's anxiety. So the better your regression equation is, the higher the SMC or R-squared value. And we actually found this already in SPSS. If we just scroll up a little bit, right in here, model summary. So you could have grabbed that back when we did the regression originally, the model summary R-squared 0.634 there. And that's again based on both IVs. Okay, so we moved into the other stuff you should know section of the multiple regression. I will allow you to pause the video if you want, take a drink, and resume, as I will do here. Hold on, I'm taking a drink. Okay, I don't know if you heard that, but I took a drink. It's just water, don't worry. Okay, so multiple regression. So we have our results and we have our betas for each of our IVs, but we don't, there's a little bit more to be done here to really interpret and really be able to compare our independent variables to each other typically. So if our independent variables are really uncorrelated with each other, they're like close to 0 in their correlations, then maybe we don't need to do much because they're so unique that the betas are going to describe their relationships with the IV uniquely, and so we're okay. It's sort of like running two separate regressions, right? You could run one regression with one IV by itself, and then do a second regression, removing that one and adding in the second IV by itself. You could also compare that way. That's equivalent to a multiple regression when both IVs are uncorrelated with each other. However, it's very rare, especially in psychology research, when you have two IVs that are completely or almost completely uncorrelated with each other. And so as long as our correlation between them is less than 0.9, we can still run the regression, right, by our multicollinearity rule. But if the correlations are somewhere between 0 and 0.9, the betas are going to kind of depend on each other a little bit. For example, if you take one IV out and put the other one in, it's going to change a little bit what the interpretation is. And so to get at that, we're going to have these additional statistics: partial, semi-partial, and squared semi-partial correlation. And so what these do is they try to parse out the unique relationships between each IV with the DV. And it allows us to do it in the context of a multiple regression, and saves us a little bit of work in, like, for example, not having to run separate regressions with each IV separately in there. We can still just do it all in one run with a multiple regression, but then when we get these statistics, we can clarify, for example, if your IVs are correlated, let's say at 0.4 or something like that, it's still perfectly valid to run a multiple regression, but these additional correlations are useful to sort of tease out the uniqueness of each independent variable in predicting the DV. So let's get into the definitions, and then if you're watching this in advance of class or maybe after class, you may know already that I like to draw some Venn diagrams to illustrate the uniqueness of or the fractions of variance that each of the partial, semi-partial, and squared semi-partial correlations assess. You can also look in the Tabachnik and Fidel book. They have those Venn diagrams in there. And so it's about separating out the different overlap of the different variables. So for example, partial correlation, the correlation of an IV and a DV, okay, just starting with a straight up correlation, after the contribution of the other IVs is removed from everything else, both IV and DV. So you're taking, for example, with X1 here, with mother's anxiety, you're taking the correlation of mother's anxiety and birth weight after father's anxiety has been removed. So it's as if dad is just no longer part of the picture, not affecting the baby, and also not affecting mom. And so you're just looking at mom unique with baby, with father, with dad out of the picture. And then you do the reverse for X2. You look at dad's effect on the baby, removing mom completely from the picture. And so we get these correlations here. Mother's anxiety negative 0.80 is greater in magnitude than father's anxiety. For semi-partial correlation, it's similar with one little twist. It's still the correlation of an IV with a DV. After the contribution of the other IV is removed from only the other IV. So here, for X1, you have mother's anxiety and its relationship with baby's birth weight, removing dad's influence on mom, but not removing dad's influence on baby. For X2, you have father's anxiety correlating with birth weight, removing mom and her influence on dad, but not mom's influence on the baby. So I've never had a strong opinion about whether partial or semi-partial correlation, which one's better, which one you should report. Usually both get reported, and usually in my experience they're kind of similar to each other. But sometimes people prefer one versus the other. The squared semi-partial correlation is the unique contribution of an IV to the total variance of a DV, and this occurs when you take your semi-partial correlation, which we just saw here, and you square it. The nice part of the interpretation for squared semi-partial correlation is that it maps onto R squared well. So this is the amount by which R squared, or the SMC, squared multiple correlation, is reduced if an IV is deleted. So this is like, what would R squared be if you went from both mother's anxiety and father's anxiety to just, let's say, mother's anxiety by itself. And so then you can see the effect of having dad in there versus not having dad in there in terms of the R squared. How much is dad really adding to the prediction of the dependent variable is assessed by his squared semi-partial correlation with the DV. So for our example, here are your squared semi-partial correlations. You can also you can see these, or you can get these by just squaring the semi-partial correlations that you've already calculated. So before I move on to that next slide, I wanted to show you where these are in SPSS. We're going to go to Analyze, Regression Linear. Again, you could have done this all in one step. If you're doing this in the homework, maybe you do it all in one step. So we're going to go here to Statistics, and we're going to get part and partial correlations. You can also get R squared change, but I'm going to leave that blank because it's optional and unnecessary in this case. So just part and partial correlations. For whatever reason, SPSS calls the semi-partial correlation a part correlation, and it calls the partial correlation a partial correlation. So not sure about that, but that's what it does. So we're going to, this is a redo of the same same regression, and all you see here is just a couple of extra columns added to the end of the coefficients box. So if you're going across on the mom's anxiety row, you go across, it adds a zero order correlation first. That's just the straight up correlation between mom's anxiety and birth weight. And then it adds the partial correlation, negative 0.795 for mom, negative 0.148 for dad, and then the part correlation, which is the semi-partial, negative 0.793 and negative 0.091. And all you got to do then to get the squared semi-partial is square negative 0.793 and negative 0.091. Okay, so here is some regression wisdom for you. This is a little interlude here into our regression process. We've now completed an entire regression, complete with our partial and semi-partial correlations. So we're going to get into kind of like special topics here for the rest of the video. The first one is, when do you use a regression? I once had a professor, and if you guys know Andy Ainsworth, this was Andy's advisor when Andy and I were in grad school together at UCLA. Steve Reese, he was a friendly guy. Occasionally he would, in kind of a surprising way, he would become very passionate about statistics, as he should be passionate about statistics, aren't we all? And he said, at one point, I remember he said something like this. He said, "I don't know why anyone ever does ANOVA. Regression can do everything ANOVA can do and more, and the reverse is not true. So why would you ever do ANOVA?" And we were all like, "Oh my God, we just spent like, you know, whatever, 5 or more years studying ANOVA. Everybody gets taught ANOVA in undergrad psychology class. Like, or did we just waste our time? What did he mean?" Well, I don't want to blow your mind like he did for us that day, but I wanted to clarify that yes, you can do a regression whenever you might do an ANOVA, but there are also some reasons why you might stick with ANOVA, and everyone in psychology is familiar with ANOVA. That's one reason itself, is that everyone is familiar with it. But when you do a regression over an ANOVA, in other words, you can do the regression approach to ANOVA. Those of you guys who had 485 class probably just did this in some form, which is with orthogonal coding, which is not always fun, but kind of interesting how it works. So when your IV has just 2 levels, let's say in an ANOVA with 2 groups, you run a regression, you actually get the same answer. You don't have to do any special coding or anything. So that's one thing that that you can do, is just get you get the same p-value, declaring that IV as a independent variable for a regression or an independent variable for ANOVA. Either way is the same. When your IV, however, has more than 2 levels, you use the orthogonal coding. That results in a multiple regression. The orthogonal coding is a way of coding, let's say, group 1, group 2, group 2, group 3, group 1, group 3, and all that in a way that allows you, again, to get the same p-value for the results for an ANOVA. For the ANOVA as you did with regression and vice versa. However, when you start having to interpret beta weights for those, I don't know if you guys tried this, for the orthogonal coding and so on, interpretation may take some extra effort, and that's where there's sort of a split here. The dangerous path this can lead researchers down a dangerous path of like, oh, well, I'm just not going to do the regression because I don't understand how to interpret the beta and all the statistics we just went through, because the orthogonal coding is kind of funky in itself. So yeah, suppose a researcher wants to avoid regression. Well, there's 2 sides to this. Now, the first side, okay, so what do you do? Like if you've already got the data and it's already set up, you don't really, it's not a big deal to run a regression with that orthogonal coding if you understand what's going on, and you can interpret it. Maybe you get your professor or your advisor's input on how to interpret. The problem comes in when you do this when you shouldn't, and that is when you're dichotomizing a continuous variable. So dichotomizing means, like, let's say you have a anxiety variable, and you're trying to cut it into high and low, let's say, instead of a continuous variable. Well, the continuous variable has a lot, and I'm giving you the answer. Why is this a dangerous path? Here's the answer. It's because when you split that variable in half, you're losing variance, right? You might have an anxiety scale 1 to 10. Let's say you split it into 1 to 5 gets a 1, and 6 to 10 gets a 2. That's dichotomizing. Well, if you have a bunch of 8s in there or 9s on the scale and no 6s, then that 6 to 10 range it's different than, let's say, if you had all sixes, right? Because those sixes are a little bit closer to fives and people that are in the lower category than the eights and nines are. If you have a bunch of eights and nines, then those people are clearly high on anxiety. The six is kind of closer to the middle. So you're lumping together all those people above six, thereby losing the variance that exists there, and thereby losing some richness in the data. Something the data is trying to tell you something with that continuous variable, and you are losing that something by dichotomizing it because you're restricting down what it can tell you. Now, dichotomizing variables sometimes is appropriate. I'm not here to say that you should never do it. Sometimes, for example, if you're trying to, like we said in the data screening video, if you're trying to cut back, let's say, a drug use variable, and you have like 10 or more times per month, and there's a person in there with 100 or something like that, you can then, worry about that person with the 100, but also you can probably safely put that person into the 10 or more group, so that you can keep their data and then dichotomize away. But if you're doing that with too many people and it doesn't make sense on a continuous scale with reasonable variance to do so, then you might try not to do that. So that's the advice for now. Don't dichotomize your continuous variables unless you're highly justified. And meanwhile, if you want to follow the guidance of Steve Reese, start doing regressions instead of ANOVAs, at least until your advisor or someone else tells you to go back to the ANOVA because it's more understandable and easier to interpret. And more than that, also, there's also a side to, like, we want to make our statistics, our very complicated statistics, understandable to someone, a psychologist, or even the public. If we make them too complicated with this orthogonal coding and stuff that nobody understands, then we're getting too far away from being able to teach what we have researched. So I'm not quite as passionate about Steve Reese about that, but it's an interesting point to cover in the regression video. Moving on, however, now to issues of suppression and singularity, and we'll finish up with mediation. Suppression and singularity are things that occur and are hard to explain sometimes, and so suppression in regression should be explained here at some point in your lesson. So here in real life, we have the act of putting down by authority or force. This is what suppression means in real and non-statistics, the non-statistics world. Excluding from consciousness, I'm not sure about that, but if you're suppressing something, right, in your brain, then you're not communicating something that you're feeling, let's say, and that's what that's talking about. So how does this map onto multiple regression? Well, what you're doing here is you're adding a second independent variable on top of a first one, and that second independent variable is suppressing that first one. It's changing the beta for that first variable changes, and that first independent variable changes once you add in the second independent variable, and you get confused. And that first variable, the effect of that first variable is what is being suppressed. Technically, it's the variance of that independent variable that is irrelevant to the prediction of the dependent variable. So that's when that beta changes, as we're going to see here in a minute. Irrelevant variance, or I guess that would be error variance, noise, whatever you want to call it, residual variance of that first independent variable is then being suppressed or excluded or kept a secret from the regression equation. And this is fine. Mathematically, it's fine, but we have to understand what it means as we go along. So this is what I mentioned. You add in a second independent variable, and it suppresses that variance, and the beta changes. And in fact, the beta might go up instead of go down. And that's when it gets really confusing because, for example, or sometimes anyway, for example, let's say you have mom's anxiety in there. It's affecting baby's birth weight by itself, just one simple regression. Then you add in dad's anxiety, and suddenly mom's anxiety is more important. What? Like, how is that? That doesn't make sense. Like, there's only one thing that it's doing. It can't be doing something that it wasn't before. Well, it's because of the correlation of the IVs that this happens. And it's another reason why we need to pay attention when we go from a simple regression to a multiple regression, or when we go from betas to semi-partial and partial correlations. Because typically, when you report those semi-partial and partial correlations, everything I think becomes a little bit more clear as far as what is uniquely happening between IVs and DVs. But meanwhile, this has been something to confuse many a regression researcher, this suppression issue. So I've got 3 examples here, or 3 kinds of suppression, and then an example here that each one I've actually seen in my own research, but we can do in class some more examples if you guys want. I've come up with some other ridiculous examples that may be better illustrating this than just my PowerPoint examples here. But classical suppression is the one that is the least kind of intuitive, and that is you add your second independent variable into the equation, causing the effect of the first independent variable to increase. So there's something, again, in the correlation between the 2 IVs that causes the beta for x1 to go up when it's in the equation together with x2. So it's kind of weird. So for example, here we have basketball playing ability, which is often my dependent variable in my research. So that's your example here. You start out with test-taking ability in your equation. That, well, it seems like it's irrelevant to basketball playing ability, right? But then you add in x2, which is a test of knowledge of the rules of basketball, or a test of basketball, which is correlated with both test-taking ability and basketball playing ability, right? You add in that x2, and suddenly test-taking ability becomes relevant as a predictor of basketball playing ability, when originally it was not. So that's classical suppression, and again, we can go over more examples of this. And we can try to wrap our brains around the concept as well as the number, the effect on the betas. So the second one is cooperative or reciprocal suppression. So this one is like x1 and x2 correlate negatively with each other. Those are your 2 IVs. But then the betas for each one go up when they're both in the equation. So let's look at the example here. We have poise under pressure, which is something I've studied most often in my research, and attention paid to the rules of basketball. So this one, these 2 are negatively related because if you're paying attention to the rules of basketball, then your poise is actually worse. If you're relaxed, then you're not really paying attention to the rules. You're just letting it flow, kind of. So these are 2 IVs that are negatively correlated with each other. But then when you add in the prediction of the dependent variable, poise under pressure becomes more important than it was before. Attention paid to the rules of basketball also becomes more important than it was before, presumably because there is pressure now. So let's say poise under pressure didn't matter at first as much because there was no pressure. Attention paid to the rules of basketball did not matter as much, but then when the pressure was added in, both of these variables were added in together, then they became more important, and the betas went up, despite the fact that the IVs correlate negatively with each other. Number 3 is negative or net suppression. And this is, I think, number 1 is probably the most common. Number 2 is probably the most confusing. And number 3 is also somewhere in between. So this is the second IV is added to the equation, causing the beta to switch from positive to negative, or vice versa, negative to positive. So that one, I mean, this one will throw you off too, because you thought your IV had a positive effect on the DV, and then now suddenly it's switched to negative. You're like, oh man, maybe I just made an error or something. Uh-oh. But it's actually fine, mathematically fine. And again, I think the partial and semi-partial correlations can clarify any confusion as you go through these scenarios. But anyway, so for this one, so you start out with attention paid to the rules of basketball, predicting basketball playing ability, and then you add in X2, in this case, is a test of knowledge of the rules of basketball. So your initially attention paid to the rules of basketball was like a negative thing, right? Because if you're playing and you're like, well, I'm just trying to play basketball and succeed, you don't necessarily want to be paying attention to the rules. But then you're forced to take a test, and so, okay, now I'm not playing basketball anymore necessarily, I'm just taking a test, and so then that flips, and now the attention paid to the rules of basketball comes in handy for basketball playing ability, something along those lines. So again, we can go through additional examples in class or in office hours or whenever you want. You can email me an example, and I will say, no, that is not suppression. No, I will say, oh, good example of net suppression. Yeah. Okay. Next one is singularity. So this one is usually easier to diagnose, but will really knock out your regression and make it impossible to do if this occurs. So in real life, singularity is a separate person or thing, or distinguished by superiority. You are a singular student. You are the best in the class. Or something out of the ordinary. Okay, so how does this apply to multiple regression? Well, this is when one variable or one IV in particular just completely knocks out another IV, and SPSS stops working, and it's kind of crazy. So this is when sometimes this is hidden. The only time that this is really an issue actually is when this is hidden, because sometimes you might, for example, throw in let's say you have two variables in there as IVs, and then you have a third variable that is the mean of those first two, right? So you have like anxiety and stress, and then you're like, oh, I wanted to create a composite average of anxiety and stress, and so you put that one in there too. SPSS will explode because it can't do that. It can't include that that average variable because it's an average of the other two. It's a linear combination. So it could be an average. It could be, in this case, 2 times x1 plus 3 or whatever. As long as those IVs are related to each other in some sort of linear way by an equation, then SPSS is going to disallow your regression. So this is sort of like the ultimate form of multicollinearity. It's when two variables are correlated, not correlated necessarily at 1, or even correlated that strongly as 0.9, but they're correlated so well by linear combination that SPSS will disallow it. So Tabachnik and Fidel, the wisdom here is that screening for singularity often takes the form of running your analysis to see if the computer balks. So that's what happens. Of course, before you get to that point, like let's say you're about to include that average or that index value in there, and you're like, oh wait, that's a linear combination of the other two IVs. Oh, then you can take that out and prevent, be proactive to prevent singularity, ideally. Okay, so I'm going to do my best to demonstrate a modest version of suppression here based on our anxiety and birth weight data. So what I'm going to do is run a regression with just mom's anxiety in there by itself without dad's anxiety, and we're going to observe the beta for mom's anxiety, which is right here in the coefficients box, negative 0.791. Now we're going to add dad's anxiety back in. This is going to recreate the regression that we already did, and we're going to see what happens to that negative 0.791. We already kind of know, if you guys remember, or just rewind through the video. It becomes negative 0.81. So in this case, the beta increased in magnitude. So I should clarify in the notes, perhaps, that increase here should be like in magnitude. So we do have a very minor, it's 0.79 to 0.81, but it's a very minor classical suppression effect where dad's anxiety comes in and impacts mom's anxiety just a little bit, or correlates with it just a little bit, which then in turn impacts mom's anxiety and its effect, or her effect, on the baby. So that's your very modest classical suppression that's occurring here in our data set. The other thing I wanted to demonstrate briefly here is singularity. So I've added in, foolishly, added in another independent variable here, which is mom's anxiety times 2. So it's like a doubling of mom's anxiety. And so what's going to happen here, if we try to include this in the regression, is that my SPSS program is going to explode. Let's see what happens. I'm going to add it in there. It's a linear combination of mom's anxiety. I'm going to click OK. SPSS, well, it doesn't explode. In fact, it just kicked it out automatically. Well, how about that? Excluded variables, and you have like mom's anxiety here. What it did was it included mom's anxiety times 2, and it excluded mom's anxiety. The result was actually the same. But so in this case, it did not explode. Maybe yours will. I don't know. And in fact, it ran the analysis, but it refused to run the analysis that had both variables in there at the same time. So that's the point. I think SPSS probably is a little bit, when there's a singularity that occurs, it doesn't react in an extreme way. It's just like, well, that was dumb to include that third independent variable. Let me do this stupid user a favor and kick this additional independent variable out of here. And that's probably what they meant to do. Okay, that's how SPSS speaks. It's kind of strange.